Hello students. Today we will learn about velocity selector and mass spectroscopy, which is related with our previous lecture where we studied motion of charged particles in magnetic field. But before that we learned about magnetism and magnetic fields itself. So we start with velocity selectors today. What before actually going to understand the concept of velocity selectors, we should understand about electric field and motion of a charged particles in an electric field. For an example, that we do have two magnetic plates. One is actually connected with a negative terminal of a battery and other is connected with a positive terminal of a battery. So this means that between these two plates, we do have a potential difference V. So one plate is a negative, other plate is a positive. So then with this configuration between these two plates, we will have electric field E, and the direction of the field lines will be from a positive plate to a negative plate. As you may remember that the direction of the electric field is decided with actually the test charge particle, and the test particle is always a positive charge particle. So then you can see if we put a positive particle between these two plates, it will be pushed by the positive plate and it will be attracted by the negative plate. So the feed lines are from positive to negative. Now, this charge particle, if we consider that it is any charge particle Q and it is actually near this positive plate, the positive plate will apply the force on it to push it away, and the negative plate will be attracting it. So it means that this charge particle will be accelerating towards the negative plate with some acceleration a. Now this charge particle is a massive particle, so it has a mass m. Okay, now to investigate the dynamics of this charged particle between these two plates, what we have to do, we have to actually apply Newton's second law, which is force is equal to mass times acceleration. How can we calculate acceleration of this charged particle? So first, let's go back about the electric field. According to the definition of the electric field strength, E, that is equal to the force per unit charge. So this is actually the same concept as for the gravitational field strength G, that is the force per unit mass according to Newton's second law. And here this E is electric field strength, that is electric field strength, and F is the force and Q is the charge. So now from this equation we can see that what the force on this charged particle Q is, that is the product of the charge and the strength of electric field. The electric field that we generated by applying the potential difference V between these two plates, that means that our electric field strength E will be equal to the potential difference divided by the D. What D is? D is the distance between these two plates, that is the distance D. So now from this we can also actually see that if we combine these two equations together, we can find that the force in terms of the potential difference, which is the value of the charge, potential difference V divided by D. So this will be the force that will work on this charged particle to move it inside the electric field. So if we combine our this equation number 2, and let's say this our equation of second law of Newton is 1. So combine equation 2 and 1, we can find that the Q times potential difference divided by D is equal to mass times acceleration. So this means that our acceleration is equal to Q times potential difference divided by the D and the mass of the charged particle. So from this equation, the last one, we can actually calculate acceleration of a charged particle inside an electric field. So I actually have this formula in terms of potential difference instead of electric field strength, because if we are going to provide the electric field strength, of course we will apply the potential difference. So this parameter will be known, the charge of the mass, so charge value of the charged particle, m is the mass of the particle, and d is the distance between these two plates. So this way we can calculate acceleration. So it means we can understand dynamics of a charged particle in an electric field using this concept. Now let's consider that we do have this field and we have a positive charge particle, and now we have the different configuration of our electric field. Positive plate is at the top and negative plate is at the bottom. So field lines from top to bottom, and this charge particle is outside the electric field, and this charge particle is moving with some velocity v, and this v is velocity, it is not the potential difference between these two plates. Now let's see that what will happen that when this charge particle moving with some constant velocity v and it enters in the electric field E between these two plates, then you can very easily see that if this actually charge particle will enter inside this electric field, this charge particle will experience a force, and that force will be equal to charge times electric field strength, and that force will be along these field lines on the positive charge particle. So it means that this charge particle will actually experience a force that is perpendicular to the motion of this charge particle. So then in the result, what will happen that this electric field force, it will try to push this charge particles downwards. So then the trajectory of this charge particle will change and it will go somewhat like this. And once it is outside the electric field, then it will go straight, actually following this at the direction of its velocity. And now, if we consider that we do have a negative charge particle, and in a negative charge particle, the force will be F is equal to negative Q, because now our charge particle is negative Q times E. So this electric field strength and then our force. So now this time the force on this negative charge particle, it will be upwards, but still it will be perpendicular to the motion of the charge particle. So now you can see very easily that this time the trajectory of this charge particle will be somewhat like this, and once it is outside, then that will actually move along the straight path once it is outside the electric field. So it means that if, for example, a charged particle enters in an electric field at 90 degree, then its trajectory will be changed. So it will get a kind of a curved trajectory inside the electric field. So now, with the understanding of this concept, that the dynamics or the motion of a charged particles in electric field, now we can move towards understanding and the construction of the velocity selector. What the velocity selector is, that this is a very simple concept, and we already understood about the motion of the charged particles in an electric field. Now, if for example, I consider that I put my this arrangement of the electric field, meaning these metallic plates, inside magnetic field, inside magnetic field. If I have this magnetic field and this magnetic field flux density is constant all over this area, and it is outside, meaning that it is out of the plane. It is out of the plane, that we can represent with these dots. So dot means that arrow is coming out of this plane. So this will be actually the way of representing the magnetic field out of the plane, meaning that out of this screen. Now we can see that if this charged particle enters in this region and it has a constant velocity v, then what will happen? That the trajectory will bend down, because the force, which force? Electric force of this electric field, I mention it with the Fe, that will be downwards. So now what we can do, we can see what will happen here, that if our magnetic field is out of plane, apply the left hand rule. The first finger of your left hand should be towards you and the second finger towards the right. Then you can see the thumb will also be downwards. So now the both forces, the force of magnetic field and electric field in this configuration, are downwards. And then it means that the both fields are pushing this charged particle downwards. This is what we do not want in velocity selector. What we want actually the force opposite to the electric field force. So it means what we need to do, we need to actually change the direction of our magnetic field. So it should be into the plane. So I intentionally did this just to remind you the direction of the magnetic field force. So now you can see that in this configuration, the force of the magnetic field will be upwards, meaning that it will be in opposite direction to the force of this electric field. Both forces will be cancelling each other's effect. So now you can see that here this field is applying the force. That force, let's say it's FB, it is upwards. Now both forces are cancelling each other. These two forces, let's write their formulas, then we can understand their effect on this charged particle. The electric force is Q times the strength of the electric field, and the magnetic force, if you remember, that we found out that this is the charge times magnetic flux density times velocity of the charged particle. Now, this means that when this charged particle will enter in this region, then it will experience two forces, one downwards, other upwards. So, if the velocity is higher, meaning that the charged particle is moving too fast, then it means magnetic force will be stronger, and this charged particle, it will actually move, you could say, upwards, meaning that its trajectory will go towards positive plate. But then if its velocity is lower, meaning the charged particle is slower, then you can see that the charged particle will move downwards. But now consider that if both of these both of these forces on this charge particle are equal to each other, then what would happen? Then they will cancel each other's effect, meaning the condition is that the electric force is equal to the force of the magnetic field. Now, in this condition, the Q times E is equal to Q times B times V, the velocity of the charged particle. So now this charged particle in this condition, when both forces are equal, will not experience any force, and this charged particle will be able to move just straight without any deflection. So it will keep its momentum and the direction of the momentum because velocity is constant. So the charged particle will be moving following Newton's first law. The second law would not work because the total force on the system is zero. So now you can see here that what is going on in this equation, when both forces are equal to each other, this charge has cancelled with this charge. Now, electric field strength is equal to magnetic flux density times velocity. So it means that we will have the equation of the velocity of the charged particle is equal to this B would divide the electric field strength. So E divided by the B, which is the magnetic flux density. So what this equation tells us, this equation tells us that if, for example, we have a bunch of charged particles and they may have a spread of the velocities, meaning that they do have a different velocities. But if they will pass through this arrangement, perpendicular arrangement of magnetic field and the electric field, then the velocity that would follow this equation, that particles will not be deflected. That particles will not be deflected. They will actually keep their motion along the straight path. But the others, they will be deflecting either upwards or downward. Too fast, going up, too slow, going down. But with the velocity that actually follows this equation, they will move straight along the straight path. So now you can see that this equation is actually the velocity selector equation or velocity selector equation. So then it means that this arrangement, using this arrangement, we can actually get the charged particles that have only one single value of the velocity. All charged particles will be moving with one constant velocity. Now, the particles that are coming out over here, so you can use this kind of aperture, meaning that there is a little hole in a metal piece or something else. So where these particles with a constant velocity, they will be able to go out and all others will be blocked. So using this equation, if you will change the value of the electric field or the value of the magnetic field, you can change the velocity. So you can select velocity, that what type of the velocity or what value of the velocity you want at the end of your this velocity selector. Now it means that by using the velocity selectors, we can obtain a beam of charged particles where all charged particles have almost similar velocity, meaning the same velocity, and that velocity will be constant. Now, why we want this, we actually will understand it at the next slide, where we want to connect this our velocity selector with our mass spectrometer. So now you can see here, for example, we have the positive charge particle, and this charge particle passes through this velocity selector. And at this point, this charge particle will have velocity, and that velocity is equal to the strength of the electric field divided by the magnetic flux density. Now, the second part of the mass spectrometer is actually a region where again we have a constant magnetic field, constant magnetic field. And if we have this constant magnetic field within this range, this time our magnetic field is out of the plane. But here in the velocity selector, you remember that the magnetic flux density was into the plane. And here it is out of the plane. When we have out of the plane, velocity vector is actually straight along this line. Then using left hand rule, you can find that magnetic force will be downwards within this region on this charged particle. And we know that the magnetic force on this charged particle, when it actually moves in the magnetic field perpendicular to the velocity, then we actually force the charged particle in circular motion. So, in simple words, you can say magnetic flux density. If the charged particle at 90 degree, it will actually apply the force. That force will provide the centripetal force. If you remember the previous lecture, we actually derived the formula for the radius of the circular path of the charged particle in a magnetic field using this equation, that the centripetal force mv square over r is the radius. That will be provided by this magnetic force value, which is equal to the q B, the strength of magnetic flux density, times velocity. So now this velocity gone with the 1 power, left with the 1, and now we can rearrange it, that 1 over r, which is the radius, that is equal to qb over mass times velocity. Now, if we flip this equation, then we can find that the radius of the circular path will be equal to mass times velocity divided by the charge times magnetic flux density. So this equation is actually the main equation of our this mass spectrometer. So here, what will happen, that you can see that we actually have selected the velocity using velocity selector. So it means we know what is the value of the velocity, which is given over here. And then this B value is actually the magnetic flux density within this region. It is not in the velocity selector. It is actually in the main mass spectrometer region. So Q is the charge of these charged particles. They can be ions of any element, and M will be the mass of that element. So then now you can see that our magnetic field that we applied, we know about that, and the velocity we have selected, we certainly know about that. And from this mass spectrometer, what happens, that when the charged particle will have the circular path and it will complete a semicircle, and it will hit here at a screen which is a fluorescent screen, and that actually create here a spot that we can see. And then from this entrance of the charged particle to this spot, it is actually, you can see the diameter. It will be the diameter, and half of that is the radius. So this total distance will be 2 times r. So it means that from this mass spectrometer, we can measure the radius r, and velocity from velocity selector B we applied. So this means that if we rearrange this formula, we can find mass over charge is equal to V divided by the radius times magnetic flux density. So this is the mass over charge ratio, or you can actually also say that this is a charge to mass ratio that we can certainly measure. Radius of this circular path times b divided by the velocity. So now here, that in the mass spectrometers, what we do, we actually mostly use ions, and we actually know that what the charge is, that we actually can say, for example, that I have hydrogen ions that will be one positive. This is the very simplest example to understand. So it means these particles will be just protons. What we know that this hydrogen has some isotopes. Isotopes. Isotopes means that it has actually the different masses, meaning that the mass number different, but atomic number is the same. And this means that we will have some particles will have one proton, but the charge will be always one positive. What, for example, they will be in this configuration, and 1 1 1 2 and 1 3. Hydrogen with one proton, zero neutron, hydrogen with one proton and one neutron, hydrogen with one proton, two neutrons. So hydrogen, deuterium, tritium. So it means that we will have ions with the different masses, but the charge will be the same. Now, when we velocity selected, velocity constant known, magnetic field known, radius has been measured, then we actually also know the charge because it is only one positive. So then what we can understand or determine, let's have a look. You see that from this equation, if we will have less mass means smaller particle. So that will be the hydrogen H11 in our example, that will have smaller radius because radius is directly proportional to the mass. Then for the deuterium, what will happen? The mass has increased because of the addition of another neutron in the nucleus. Then now we will have our deuterium spot over here with the bit bigger radius. Then the third one, that will be the tritium, meaning that it will have a higher mass, 1 3 over here. Okay, so it means that we can actually investigate the masses of the particles, and also we can know about the isotopes, that how many isotopes a element has. So what kind of a data we see from these modern mass spectrometers? We actually get a graph, and that graph is mostly like this, that charge to mass ratio. Sometimes we write like that, or you can also actually see the mass. For example, here you can get a peak, and then you can get a peak, and you can get a peak. For example, it says that this peak indicates, let's say, in just for understanding, that this is hydrogen 1 1, and this one is hydrogen 1 2. The third peak is hydrogen 1 3. Now you can see here that the peak of hydrogen 1 is bigger compared to the peak of hydrogen 1 2, and peak of hydrogen 1 2 is bigger than the peak of hydrogen 1 3. It means that in nature, by this actually the graph, it will say that this isotope is abundant, meaning that it is more available compared to other isotopes. And then with this height, we can actually also measure the percentage abundance of elements, meaning that what percentage of that element is available in the nature in one element, meaning that this isotope, what is the percentage abundance of that element, sorry, of that isotope in a sample of that element. So this is actually a simple, straightforward concept of a mass spectrometer. So this is actually the very beautiful application of electric field, of motion of a charged particle in electric field and magnetic field. So we actually also understood today that the electric field can accelerate a charged particle, but the magnetic field only bends its path into a circular path. So this actually, the knowledge helps us to develop the mass spectrometer to investigate the isotopes or the mass of the charged particles. So I hope you understand the concept of dynamics of the charged particles in electric field and the concept of velocity selector and mass spectrometer. If you have any question, you can actually leave the question in the comment section and we will reply to each and every question. Thank you very much for your attention.